I'm pleased to introduce my former student, Souvik Goswami, to talk on higher arithmetic Chow groups.
Thank you, James, and thanks to the organizers for inviting me and letting me give this talk. In principle, this talk is a prelude to what Jose talked about a couple of weeks back. There we talked about a special case of height pairing for higher cycles. And hopefully today what we are going to see is a general version of that. So if you are present in Jose's talk, you will be able to connect the dots, or he will give another talk later this month, then you will be able to connect the dots. Okay, so to set the notation, so x will denote a smooth and projective variety over a number field K. So for such a variety, Gillet and Soule, they define this arithmetic Chow groups and the arithmetic K groups with isomorphisms after tensoring with rationals. Now, the idea is that given blocks higher Chow groups, which I am going to define, can be defined an arithmetic version now there are two sides. One is blocks higher Chow groups, and on the other hand we have the K groups. And so what the Takeda did, he defined a version of higher arithmetic K groups, but I mean, to my knowledge, till now there is no known isomorphism. Like, I mean, this is something we need to establish. Okay, so this is the part I'm going to be interested in. Okay, but before we proceed any further, let me say the following. So Burgos, along with his student, they have already introduced a version of these groups. Let's call it Burgos value, such that they fit in a long exact sequence. So they have already a definition of this groups which fit into this long exact sequence. But this wasn't pursued any further. So in principle, all such groups will be okay, so in principle, given, let's say, a complex, this computes the motivic homology, and another complex, let's say T, which computes something called the link homology. Suppose you have a map of complexes which computes, say, the regulator, a version of the regulator, then you can take the homotopy fiber of this row and declare this to be your favorite objects, either this or. So this was the general principle, and it was on this principle that these Chow groups by Burgos and his students were based on, and they satisfy a long exact sequence. But the problem with these groups are that they have everything. So one of the most important things that they satisfy is that they are homotopy invariant, so they don't depend on the complexes. They have a product, they have push forward and pullbacks, but the products are not very well suited for computation. It comes from homological algebra, so it involves a lot of simple complexes like diagram chasing. So when we started this project of, so our basic aim was to compute something called a higher height pairing. And to compute that, we needed to really get hold of higher cycles, and some form of, let's say, some green form type objects to it. So we needed a very concrete shape of this product. So then what we did was to define another version of arithmetic Chow groups, which is more akin to what Gillet and Souvik did. So let's get on to the So what do we need? Higher groups. So we want the QSL version. So what we do is we take we need to fix some notations. We do not need this part. We want to max. These squares. These are the two face maps. Which, okay, so let's say free abelian group. Generated by cycles. intersecting properly the faces, and also have this property that delta 1 I star of C equals 0 for all I. So these are what we call free cycles. So elements are called free cycles here. Now we also have this boundary map delta from C. So if delta C equals 0, then Z is a cycle. Is a higher cycle. And finally we define this to be the homology of this particular complex. Well, that's the definition of higher Chow groups that we are going to use. So this is in some sense the motivic part that we need, but we also need informations coming from complex geometry. So here we can assume x over c is projective. Then let this denote the same complex of C infinity forms. Observation. And this is the corresponding real complex. With the twist, this will be the notation. Okay, so once we have this complex, we can associate the Deligne-Beilinson complex to it. So this is computed by the simple of the following morphism. Now, so we know that H so this computes the real Deligne cohomology of X. Now, So this is one of the complexes that computes the link homology of X. There can be several complexes which computes the link homology of X. And the higher arithmetic Chow groups that we are going to define, it's not homotopy independent. So it will depend on one complex or another. So the complexes in some sense will guide us to the higher arithmetic Chow groups. Let me tell you, so this is one complex. We can call this 1. Number 2 is the Deligne complex. Which is defined in the following way. X. So this is if n is less than or equal to -1, and it's simply n p n is greater than or equal to 2p, and one can show that in this complex of HQ it also computes the Deligne homology of the real Deligne homology of X. Now, the issue with this complexes is that in general, at the level of complexes, both 1 and 2, they are graded commutative, but associative only up to homotopy. So they are not associative at the level of complexes. But for the purpose of our higher arithmetic Chow groups, we really needed complexes which are associative at the level of complexes. So for that, if you are not bored right now, I'm going to introduce another complex. So this is called the convolution complex. Okay, so let's fix L0. So this computes the algebraic Dirac homology of the real line, and we define the following complex. in some sense it controls both the FP part and the real part in one complex. So this complex, remark following property once again we have Hn and P, this complex is graded commutative and associative at the level of complexes. So this is the complex which will form the complex geometry part of our theory. So associated to X, we now have two things. One is the complex which computes the higher Chow groups, and another complex which computes a suitable complex which computes the real division of X. Okay, so a little bit more. Similarly, so if we consider the complex of currents, if Dx is the complex of currents, then we can consider the geometry complex of So instead of forms, we just have currents. So let's see a couple of examples. One would be the standard, so take y subvariety in x with dimension p. Then we can define the current P by integrating on y and the corresponding geometry element is simply 1 times get to y. So this is one example. Another one would be the following. So this was defined by various persons, Chow and Wang. So these can either be called Wang's or Chow's forms. The chronology maybe. So let W1 be the following Tom Whitney element. So this belongs to V1 twisted by 1, while if you take the Tom Whitney current, so this is epsilon 2. This current, this belongs to there's a current defined on all of P1 because of the following property. So
like that's TT bar in the last thing?
TT bar is. Okay, so this is W1, so we can define Wn are the projections, and so these are the, so this Wn is called the conchata for the Wang's fonts. So these are the Wang's fonts, let's see. And they have the following properties. So Wn restricted to this is 0, and hence we can define the current which satisfies the following residue formula. So this is one property in between, which is 0, and this is going to be much like the higher cycles. But now you have to push forward instead of taking the pull back. So this is the residue relation that the Wang's form has. Okay, so these are the two primary examples of forms and currents, commutative forms and currents that we will consider. Now, we have almost all the ingredients, bar 1. Still complex geometry. Okay, so the last thing that we need is the Goncharov's version of the regulator. Okay, so we can define a morphism from ZP twisted by P in the following way. So we take a cycle, then map this to P1 star. So this product is in the Tom Whitney complex, And P1 and P2 are the projections. So this is a prism of complex. Prism of complexes, and number 2, one can show that at the level of Chow groups, this P computes what is called the Bateson regulator after composing with K groups. Okay, so now we have all the ingredients to define our version. Okay, so once again, we let x over k a smooth and projective variety over another field k. Let's dimension d. Okay, so x is defined over k, then the Bloch's Chow group can be computed pretty easily, but to do complex geometry, we need to find embeddings of x inside the complex case, I mean the complex plane. So then what we define is the following. So our x infinity is given by these disjoint unions. We have an antilinear involution, and we define this real analytic variety to be this manifold, you can say, yeah, this analytic manifold or real manifold with this antilinear involution. So forms or currents here will be, the ones that we consider will be fixed by this antilinear involution, so that we can compute the real Deligne cohomology of X considered as a field over K. Okay, so now this thing done, we define. So these are the higher arithmetic cycles. So this is given. You see. So this is a higher cycle, and GC belongs to D tilde. So this is D star, D one. So this is, well, let's fix connotation. So D tilde will be P modulo the image of the map. So then this satisfying DGC plus this Okay, so d of gc plus the Koncharov's regulator gives you a smooth form. Okay, so if you know a little bit about Gilles-Soulet's Chow group, this is exactly the same scenario. In that case, a green current is a current which satisfies this plus delta of C equals a smooth form. So this is more or less a generalization of what Gilles-Soulet did. So this is the GZs are called green currents for Z. And as with the usual arithmetic Chow groups, one can show that given a cycle and given two green currents for the cycle, the difference is once again given by a smooth form up to this boundary. A little bit more we need to mod out. So this we define JV the group generated by delta Z prime minus P of Z prime where be clear about it and V belongs to okay, so once again, if you recall how the rational equivalence was defined, or the arithmetic rational equivalence was defined for Gilles-Soulet Chow group, it's exactly a generalization of that. For Gilles-Soulet, it was divisors of a rational function f and the current associated to the log of mod of f, and then they also logged out by this del u plus del bar v. So this is the higher rational equivalence in that sense. Since here in this code, we define the higher Chow groups to be the quotient. Okay, so this is the higher arithmetic Chow groups that we defined in our paper. Then, of course, we need this to satisfy certain properties so that we can compute at least some examples. The major property will be the intersection product, but before that, we have certain maps. So these are cycles inside. And is given by, okay, so if you take a class, you map this to P of GZ, yes. I mean, I should probably just omega C. Omega C. But it's not a big issue. So we have theta. Then mapping to force the usual Chow group. This map E, which so you take a form and then map this to this element in the higher arithmetic Chow group. Okay, so once we have all these maps, we can define an exact sequence. Exact sequence of the following forms, HP. This is the pale instance regulator 2. So this is the map A, this is the map okay, so
Does you have the same CH?
same,
That be, there has to be.
oh, so we have an exact sequence instead of a long exact sequence in this case. But what happens is that if we define this to be the kernel of this map omega, which I believe, this map omega, then one can show that this group is isomorphic to what Burgos and Feliu defined previously. So this particular group is invariant under homotopy and it satisfies the long exact sequence that I have written at the very beginning. But our groups that we have defined are not homotopy invariant. So depending on complexes, one can get one higher arithmetic Chow group or another. The complex that we are using, of course, has the property that it's associative and very commutative, so it will help us in defining the intersection product in a nice way. Okay, let's go to intersection product. Now, if you recall Gillet and Soulet's definition of the intersection of their arithmetic Chow group, there are two intersections. One which comes for the cycles, which is okay. I mean, it comes from K0 of X, but the other one, the intersection between two green currents. So if you take two cycles which intersect properly, then the star product of green current of those two cycles was defined using a green form of logarithmic type. So we need to define something similar here. So green form of log type for a cycle. So we want this to be so how do we define that? So the form of block type is an empty group of forms in our case. So we use this notation. You can see. So we have this bunch of forms. This belongs to zero. Okay, so all these forms, so if you pick up a form Gi, which lies in this particular homotopy complex, so it is a differential C-infinity form on x cross this box I minus the support of z considered now in x cross zi. And here it has logarithmic similarities. So I should probably put log to indicate the logarithmic similarities. So not only that, it should have a staircase relation. That is fine. So if you take the current associated to Gn, then this is minus delta z minus 1 to n minus plus 1. Third property, smooth inside dtp minus n of x. So this is, the principle is that it acts as a staircase. So the current leaves inside these 2p of x cross p1 to the n. On the other hand, this smooth form is omega z, which computes the real regulator of z. This lives inside this belongs to so they live in different spaces. So one needs this bunch of forms acting as a staircase to go from this current to this form on X. Okay, so this is what a green form of logarithmic type looks like. I have just enough time to define the product and connect it to our project, or what Jose talked about a couple of weeks ago. So now the product. So now let's set the cycles that intersect properly. Okay, so associated to this cycle, and let GZ and GW be currents to the two cycles. Now one can find a green form of log type such that the associated current, so this is defined as summation E1 star G J WJ. This is same as this W up to boundaries. Okay, and this current associated to the green form, it's the green current for the cycle W. In general, for a cycle Z, we can define this current, and it's a green current for the cycle Z or W. And I mean, one can find such a green form since that the current associated to the form differs by a boundary from a choice of green current. Okay, so then we define this star product GC to be equal to the following. So I'll explain the notations. J from 0 to M, P1 star. So we take the cycle associated to Z, take the product with Wn, Gj and Wj, where of course we have this Gw as a green form of log type for W, plus we need to take the product with the green current of Z with that of the form computing the linear homology of W. Okay, so this is the star product. So now we can define at the level of Chow groups. So we take two elements here represented by cycles which intersect properly. Okay, so this defines an intersection product at the level of arithmetic Chow groups. Okay, so in a few minutes, what do I have?
You have 7 minutes.
7 minutes?
Yeah.
Okay, so this is the product, and now there are various things one can do. One of them is to define the so-called higher height pairing. Okay, so let's do that and connect it to what we are doing right now. Okay, so what do we need? Let Z be CP% and W cycles intersecting properly. Also, we need that and the real regulator classes of Z and W are 0. So then and also let this numerical condition be satisfied. So for example, if n and m are 0, this is exactly the condition for the height pairing, values inside. And let phi be so the setup that we need is x over c here once again. Phi is the projection, so then we define this pairing okay, so we can choose both green currents, GC and GW, such that D of GC so the smooth fonts are 0. So that's what we get out of this real regulator being 0. So then we can define this Archimedean part of the pairing to be simply this push forward of the current given by the star product, and we view this inside H1, the lane of X since this is closed, we can do that. So we view this inside the H1 delete. Okay. So this is our definition of higher height pairing. So I end here by noting that now with Burgos and Greg, what we are doing, so we know that for the usual Archimedean height pairing, so there is an interpretation of that through by extension of mixed Hodge structure. So a mixed Hodge theoretic interpretation of the usual height pairing. So in the current project, what we are doing is something similar in a very special situation. So once again, if you were present in Burgos' talk, so he took n and m to be 1s, and for that scenario at least we can interpret this Archimedean height pairing in terms of a mixed Hodge structure. Now you have to define it appropriately. So that's what we are doing. Thank you.
Questions, anyone?
I would just have a comment, is the reason to do that is to get away from that real regulator 0 condition.
Yes. Yes. I mean, yeah, the mixed Hodge structure that we are able to define doesn't depend on this real regulators being 0. So it can be defined more generally for any two higher cycles. In case the real regulators are 0, then an invariant of the mixed Hodge structure can be shown to be equal to this higher pairing.
I think you said that on that previous definition of arithmetic higher Chow groups by Burgos and there was a product that's basically defined using homological algebra. Okay. How does this, given that you can include those as the kernel of omega integers, how do these two products relate? Do you know that?
I think they're same up to defining the. They're the same.
Okay, so in particular, if you take two things in the kernel of omega and you take your product,
Mhm.
get something else in the kernel of omega.
No, you get the same result. I mean, this is most to be able to compute it because with this you can use currents and it's much easier to make specific computations. But the product is really the same.
Yeah,
because it's the only product.
and Burgos and in this paper it was defined using the differential forms. And I mean,
Can you compute examples? I mean, so in some cases, in bidegree 2 and n, we recover Julie Soule, I understand. But in other bidegrees, if you just look at the part corresponding to Milner case, we just a point, just a field.
yeah. So that's I didn't mention it because I wanted to mention this part. Is that we can. Have few computations and it's example, if you take x to be k, then up to n. So this is isomorphic CQ if p equals 0, n equals 0, of course, then CQ q to the r1 plus r2 if and R1, R2 are the distinct real and the complex embeddings. And 0 otherwise. So this, together with the exact sequence of higher arithmetic Chow groups, dictates the following.
So this is a computation which you just get, I guess, from comparison with arithmetic cases.
Yes.
So integrally you don't get nothing new. You cannot do any say about integral structure which was not detected by arithmetic case theory. You just compare to that and
So yeah. This is but the most interesting part is the following. So it's CHP, it's 2p minus 1 in case n is of course 2p minus 1, and then it's isomorphic to the other extreme. So this, yeah, as you said, comes down from the fact that the Borel's K group, they, in even degrees, tensor with, they're torsion. In odd degrees, you have this isomorphism because this part then goes away. So this is an example we have, and also we have some intersection pairing for such, x equals spec of k, which comes out of dialogues, block-Wigner dialogues. And interestingly, when we are computing this higher Archimedean pairing for n and m equals 1, we are also getting dialogues out of it. So, but that's it.
Okay, any more questions? Let's thank the speaker again.